Given, the root of a binary tree. Each node sits at a position, row, column. The root is 0, 0, a left child of a node at r, c, is at r plus 1, c, 1, a right child is at r plus 1, c plus 1. Return, the vertical order traversal, a list of the columns from leftmost to rightmost. Within each column, list node values from top to bottom. If several nodes share the same row and column, order those values ascending. Constraints: 1 to 1000 nodes, 0 equals val less than or equal to 1000. Under each node, the label is row, column. We read columns from left to right. The leftmost column, -1, has only 9. Column 0 has the root 3 on the first row, then 15 below it in the same column. Column 1 is 20. The rightmost column, 2, is 7. Stacking those column lists in order gives the output line. We walk columns from left to right. Within one column, shallower rows come first. If row and column match for 2 nodes, break the tie by smaller value. Tag every node with row and column. The root is at 0, 0. A left child is 1 row down and 1 column left. A right child is 1 row down and 1 column right. Here we add a right child to 1 and a left child to 3. Bucket by column, -1 holds 1. Column 0 lists 2, then 0 and 4 on the same row. Column 1 holds 3. Same row and column, like 0 and 4 here, sorts by value. Nodes 0 and 4 share the same row and column, so list the smaller value first. Collect triples of column, row, and value for every node. Sort by those keys. Then merge into one list per column. First, tag row and column with a depth first walk. Visit the root at 0, 0. Recurse to the left child, 1 row down, column -1. Backtrack, then the right child, 1 row down, column +1. The same recursion fills the deeper nodes. Notice nodes 5 and 6, both sit at row 2, column 0, the same coordinates, even though they are different branches in the tree. We do not need the tree shape anymore, only a list of triples, column, row, and value. Here they are, out of order. Next we line them up with the sorting rules. Rule 1, arrange by column from left to right. That groups the vertical strips. Look at column 0, 3 nodes share it. Who comes first? Rule 2, shallower rows come first, so the root moves ahead of the deeper pair. Rule 3, if row and column match, smaller value comes first, that is why 5 appears before 6. Finally, cut between columns. 5 groups, left to right, match the vertical order traversal. Let n be the number of nodes and h the height of the tree. Time is n log n, a depth first walk gathers n triples in linear time, and sorting those triples by column, row, and value is the bottleneck. Merging into column lists is then a single linear scan. Space is order n for the triple list and the grouped output, plus order h for the recursion stack. On a skewed tree h can be n, so auxiliary space stays linear overall. Main routine, vertical order traversal of a binary tree. If the tree is empty, return an empty list. Start a list of triples, column, row, and value. Run depth first search from the root at row 0, column 0. Sort triples by column, then row, then value. Build the answer as a list of lists. Track which column we are filling. Scan sorted triples in order. If this column is new compared to the previous one, start a new inner list with this value. And remember the current column. Otherwise we are still in the same column. Append the value to the last inner list. Return the nested lists. Helper, depth first search records every node. Nil node, nothing to record. Return from the base case. Push column, row, and node value onto triples. Recurse left, 1 row down, column -1. Recurse right, 1 row down, column +1.